Okay, let's see. Try and wait. So I didn't grade the homeworks yet either. So, and if probably grade them tomorrow, I think, but anyway, so I think I wanted to kind of finish the surface chapter today. So the first part of this, there's three things. This is Thomson's equation, which has to do with particle size, like in other words, condition to make small, like nanoparticles is always a deep quench. So it's like there's three ways to kind of talk about that: a temperature quench, a pressure quench, and a concentration quench. So that I'll go through those three. And then this business about nucleation, how thermodynamics of nucleation has to do with surface term. So it's in this chapter too. And then homogeneous and heterogeneous nucleation. So that's what the homework's on that, this part. And then there's some stuff on gas absorption measurements to get surface area. And then the Langmuir equation and the VET equation. And then I guess that's the third thing. Oh, there's a fourth and a fifth thing: block copolymers, phase sizes, and finally about this correlation function thing that I mentioned before. Well, it has to do with surface too. So yes, there's a few things to go through. So there's an idea like you have an equilibrium condition, thermodynamic condition. When you have a surface, like say you have particle size and it's an infinite particle, then there's no curvature to the surface, and then you just have, that would be like the equilibrium vapor pressure, say, for a gas, right? And then if you have a droplet that's smaller than that, so a droplet that's small or nano size, the pressure of the droplet increases, following the Laplace equation, but there's an equilibrium set up for that droplet. So in other words, you can have an equilibrium for an infinite surface, but you could also have an equilibrium set up for a small, tiny droplet. The small, tiny droplet is different than the surface. Right? So basically, the pressure inside a tiny droplet is much higher than when it's a liquid in a cup or something, like water in a cup or a raindrop. Like the pressure goes up substantially due to the Laplace equation. So anyway, so you do an equilibrium on that small droplet and then find out. So you could say say you're going to form droplets under a high pressure condition, then you'd make small droplets. It's another way to look at it. It's like if you wanted to make small droplets, you would have to make a high pressure, like a deep quench, kind of like go far from equilibrium, and you get small particles. So there's three of these equations: one for pressure, one concentration, one temperature, and they're the pressure one is called the Thomson's equation. They're all three of them are the Gibbs-Thomson equation, because the Thomson equation and the Gibbs equation are talking about the same thing: small particles far from equilibrium. Right. So, but in terms of pressure, so if you do your like the squares, you have the free energies VDP, TDS, and if it's at adiabatic, so then you have just VDP as a free energy. That molar free energy is a chemical potential. You have VDP. If you have a droplet that's the equilibrium between a gas and a liquid, then you have this equivalence. The two chemical potentials have to be the same, so you have that equivalence, right? And then if you can also write, so for this pressure, you can also write the Laplace equation, which is delta P's 2 times the surface tension by R, and you can take a derivative of both sides. So you can substitute the dP here with these volumes of the gas and liquid. So you can kind of do a substitution here and end up with this equation, dP of the gas. So dP of the liquid is V of the gas over V of the liquid. So V of the gas over V of the liquid. And then dP of the liquid is V of the liquid over the liquid. So you can say dP of the gas times that is the same as that by substituting in the equilibrium condition. And then this side's the differential of the Laplace. And then if you say that the gas volume is much higher than liquid, so you can forget about the liquid volume. You can just say, and then substitute for the gas volume, ideal gas, RT over the pressure of the gas, and you get dP gas over P gas. And then still derivative of the Laplace over here. Integral, that's ln of the P, so ln PG over P infinity. It's going to be this V over RT times the Laplace term, right? Which gives you this kind of definition that if you want to make small particles, you have to have a deep quench in terms of the pressure. There's going to be exponential the particle size, 1 over the particle size versus the pressure quench. Right. So you can do that same thing with concentration. So this thing, like if you're talking about water droplets, or you can talk about air bubbles in water, like when you boil the water. So if you do a temperature quench, so say you have water at 100 degrees C, then you quench it to 50 degrees C. You make it'll make really small, like nanoscale droplets. So if you can do a deep quench like that, those nanoscale droplets have such a pressure differential that they aren't stable. So basically, even though you're in the phase where you'd make a vapor, it remains a liquid. So you can make a super cool liquid that way. So you have a vapor going to liquid, a liquid going to vapor. Because of these pressure differentials, you can make super cooled liquids or superheated. You can make superheated liquids. So you can make it should be a vapor, but it's still a liquid. Right. So it's the kind of condition where if you put any kind of perturbance, it'll just explode, basically. Right. So anyway, so to get so there's another equation that's like that for this T jump. It's like the same thing as the T jump for the Thompson's equation, which is done kind of the same way. So for the gas phase, you write Bg's dVp minus SDT. So, and then for the liquid phase, it's incompressible, so this volume term drops out. So you just have that equals that, and then you end up with the delta S. Delta S is delta H over T. So you can substitute that and get delta H dt over T. And on this side, you have VdP. So you'll end up, if you substitute for the ideal gas for the V, it's a PV. So V is RT over P. So you end up with R, and T comes here. So you have T over T squared on this side, and then P over P on that side. Then the gas constant and the delta H term. Then you get that differential equation, which you can integrate. This gives you 1 over T, and that gives you 1 of P. So if you work it out, so P gas from let's see. dP gas. So you substitute dP gas for the Laplace equation, which is delta P is 2 sigma over R. And then you have a P gas here. Let's see, the P liquid comes from 2 sigma over R. Is that P gas? And T gas. Somehow this works out. I did it before class, but I don't remember how to get that. But basically, this just leads to this. And if you integrate this, you get 1 minus T, 1 minus T, and then this expression that gives you that the vapor for small particles. If you have infinite particles, you have the bulk vaporization, but the particles get to be so small, the vaporization temperature gets to be higher, basically because the pressure builds up in the droplets. So again, like if you have a big temperature jump, the bubbles or the droplets will be very small. Right? If you do a T jump either up to boil or down to condense, the further you get from equilibrium, the bigger the smaller the particles get. So basically the theme is that if you want to make small particles, you have to go very far from equilibrium. So then this is the concentration game. So the Ostwald-Freundlich equation says, and this is the equation that was used to make like photographic film with really small nanoparticles, right? So basically, I mean, they figured out that in order to do that, you need to have a deep quench into concentration. So you'd start with like a salt, like silver chloride, and then you try to make silver acetate, I guess. So they get a huge concentration of the silver chloride into solution, and then all of a sudden do the reaction to precipitate the other phase because of such a large differential in the concentration, you can make tiny particles. Right, so that was like controlling particle size for film. That's where this was originally. That's where I saw it was applied originally. But anyway, so in this case, you got anyway, there's a differential Laplace equation like on the other one. And then you can talk about equilibrium between the two phases and write the chemical potentials in terms of the dP and substitute in the Laplace for that, and then integrate this, get this equation, and then if you know that the surface tension, that the chemical potential is given by the Boltzmann equation, right? RT ln of concentration or activity, and then basically just using that equation and plugging that in, you get this log expression for the concentrations versus the surface tension by size, and take an exponential, you get the Ostwald-Freundlich equation. So that's another way to, so the Ostwald-Freundlich is another form of a Gibbs-Thompson equation in that deep quench gives you small sized particles in terms of temperature, pressure, concentration. And then you can also do this in, and this thing's going to be what's used for Ostwald ripening, because to say that smaller parts, so this is basically the same equation for Ostwald ripening, that you have 2 times the surface tension by R gives you the chemical potential difference. So it's the same equation that's like right here. 2 surface tension volume by R gives you the chemical potential difference between a large and a small phase. So the larger phase will have a lower chemical potential and it'll grow. This is the Ostwald ripening equation that governs the growth of large phases over small. Right, so this is along the same line of reasoning. Anyway, so there's a whole family of like things that go along with this, right? And then it's also kind of in keeping with this business. So this is the homework is on this thing. So basically, if you're at say if you have a particle of a certain size, then you have the free energy for that particle, which would be like a Helmholtz free energy, right? H minus Ts type energy. And then that's a bulk energy. But if you add in a surface term, you have to have the surface area, like for a sphere, 4 pi r squared, and the surface energy to that. So you have 2 terms. This term, if this has r squared, you have to have r cubed here because that's volumetric. So this would be the actual free energy of a droplet. And this is the volume of a droplet, and that's the volumetric free energy of infinite size. And this is a surface free energy, which is per area. So you need an area. So you have r cubed, r squared. So if you can, so it's possible to take the derivative of that and then set the derivative to 0 and find out what the maximum free energy for that. So in other words, the free energy change for making that phase, again, make the phase into a solid from a liquid phase. You're precipitating particles from a solution. And then there's the free energy difference between the liquid and the solid isn't constant with particle size because this is particle size term. So basically, as you march through that, this equation, the derivative of that's going to have a maximum at the maximum of this. So when you get to really small particles, the free energy change due to the bulk drops because it's R cubed, then the surface term dominates. When we get to really large, the surface term disappears and you have the bulk term, and they compete against each other. So this is a positive contribution, this is a negative contribution, it's phase separating. So this is dropping, that's raising. This drops faster at small r, this increases faster at large r. So basically you get a maximum in this. If you take the derivative, set it to 0, then you can solve for whatever R value that would give you. So it would give you, for homogeneous nucleation of a 3D particle, you get, if you solve that for what the R value is when this is equal to 0, the derivative, then you get R star, which is this thing. Okay, so that would be the size of a phase at the maximum in the free energy. So it's called a free energy barrier. So if you make particles smaller than that, then every time you grow the particle, the free energy drops. I mean, larger than that, every time you grow the particle, it drops. Make particles smaller than that, growing the phase won't happen because the free energy change gets larger and larger as you get bigger particles. So it wants to make smaller particles to reduce the free energy. Right, so there's a critical size above which phases will spontaneously grow, below which they disappear. Right, and if you take that magic R value and plug it back into the original equation, you get the free energy of a homogeneous nucleation of a phase, which is G star. Right, so anyway, so G, because it's 8 delta H minus T delta S, this G depends on temperature, which means that if you do your phase separation or production of particles from solution at different temperatures, you get different critical sizes because the free energy term is different. You get different critical free energy. So as you cool it down, so this is assuming it's a UCST, phase separates when you drop the temperature. So as you cool it down, this barrier drops. There's a log term of that. And then at the same time, this critical size gets smaller. So the further you get from the precipitation equilibrium point, in other words, when T equals T, whatever, critical phase separation, or this is 1, then basically you're seeing the it's easier to make the phases, and the phase size that you're making is smaller. So the deeper the quench, the smaller the phase. Same theme, like deep quench leads to small sizes. And so this is the first thing that Gibbs did, I think, for looking at phase separation, like making particles, adding in the surface term, and then figuring out you're going to get a critical size of formation. Then so that's homogeneous, like a 3D particle is forming. The other way you can form a particle is if you make something on the surface, right? So well, in one case you're forming like a simple cubic or something like that. So you have like R cubed. If you already have like dirt, then you're going to form, the way they look at it is you form this thing R. It's got a thickness T. So T is like a lot less than R. You're going to, this is heterogeneous. This is homogeneous. So this just happens, like you have a beaker, and then all of a sudden things form it. And there's going to be like a nucleation rate to that. In other words, in this case, you have a beaker, it's already got stuff in it, dirt. And then when you form the phase, it forms around the dirt. It's just two different kind of separation. So when So this would be like I mean, you could also add a nucleating agent. The nucleating agent should help form crystals, form particles. Like that's why they call it a nucleating agent. So the dirt can be a nucleating agent. So in that case, this starting equation changes. It's not r cubed anymore because you're just making a surface layer of thickness t, and t smaller than r. Right, so you have tr squared times pi gives you that's like a disk on top of the surface, say. And then the amount of new surface that you make. So in this case, this surface is the same as that surface, right? So the only new surface you make is right there. That's like t times r. It's just much less surface that you make, almost nothing. It's just a little edge. So you have 2 pi RT. You can take a derivative of that, solve for r. You find out that the r size you make for heterogeneous is half the size of the homogeneous. Right. So basically you're getting by with a lot smaller particles, like half the size particles. And roughly, and the energy is even better. So if you plug in the R star into this equation, then you solve for G star, which would be the barrier energy. So there's also a barrier energy with a peak in it, just like that. For the surface one, if you plug in that number into this equation and then solve for the heterogeneous energy barrier, then basically that's what it is. It's going to be much smaller because it's 9 over 80. So you have 9 over 80, which is less than 1. And then the thickness, R hetero is much larger than T by definition. So that's much, so that times that gives you something a lot smaller. In the end, depending on how you do this, it can be a half of the other one. But basically here, the way this is done as a disk on a top of a surface, it ends up being some 9/80ths or something there. So it'll be like 1/10 almost of the other one. So it's much smaller to nucleate heterogeneously than they nucleate homogeneously. There's no barrier, right? So that's why if you have a situation, that's why when you have heterogeneous nucleation, there's no homogeneous nucleation happens. It just depletes. Everything runs those particles and forms phases. You don't get homogeneous nucleation happening when you have heterogeneous opportunity. So let's see. This is the same thing. So this is in all the books. I mean, if you want to, this is in every book on surface, like this kind of business, and that business about homogeneous and heterogeneous. There's a bunch of books on the webpage. I don't know if you want to read about it, but like our book goes through it. Actually, our book doesn't do a very good job of it. And then let's see. So there's like I guess this book has it. This says surfaces. What are the ones I'm thinking of? Surface science would have it. Adamson has it in it. Heimitz has it in it. The same, basically that same derivations in all these books. I guess that's the point. Surfaces has it in it. So you can see if you don't like one of them, there's like 10 other derivations of that same thing. I guess those are the main ones. I think in the notes I say something about like where this stuff is, but anyway, so this kind of approach can give you another Gibbs-Thompson equation, which is this business of this, like the particle size goes with the temperature quench depth. So you get smaller particles with a deeper quench. So this is called the Hoffman-Lorentz equation, sometimes in polymers. And this is called the Gibbs-Thompson equation generally. If B is 2, it's the Hoffman-Lorentz equation, because in a polymer, make lamellar crystals and there's 2 main surfaces, like the top and the bottom, the side doesn't matter. So in their high energy surfaces. So this is for homogeneous nucleation. B is 2 for polymers and B like 4 for this cubic thing I drew on the board. And then it could be up to 6. So it's kind of 6 to 2 is what B is here. It's a geometric factor, like how many surfaces are in the thing. So you get that. Let's see. I'm not sure it gave me the new set of slides here. Some of this is new and some isn't. Anyway, so if you have an infinite crystal, let's see, this thing's derived somewhere. This isn't exactly deriving it. Let me skip through this. I think it's at the end of this. That's the same as that of the slide. Nope. All right, so that was it. No, this guy didn't update, but so you have this, you have an equation for this would be like the bulk. So if you have H minus Ts and S is delta H over T infinity. So if you don't have a surface, this term goes away and the energy term is 0 if it's at equilibrium between the liquid and the solid. So then you have R cubed times delta H minus T delta S. They're both volumetric terms. And you substitute delta S, minus T delta S, and that equals 0. So if you solve for delta S, you find out it's delta H over T infinity for the infinite one. So you can just substitute delta H over T infinity for T delta S here. And you have T delta S delta H over T infinity and delta H. So that's just delta H over T infinity times there's no T infinity here, so times T infinity for the first term. Then there's a T here, so times T there. So it's delta HF over T infinity minus T times R cubed. And then there's also this surface term, and B would be like the number of surfaces of R squared. In other words, if it's lamellae, it's 2. And if it's cubic, it's 4. So, and then gamma is the surface energy. So then you just have that equation that's set equal to 0 and solve for R, and then you get this Hoffman-Lorentz equation. You rearrange it and get the Hoffman-Lorentz. You get the T delta T minus T, and the T infinity is up here. Delta H is down there, sigma is up here. So B. So basically that tells you that if you want to get small particles, you have to have a big delta T, big quench. And you get smaller and smaller particles, the bigger the quench. It's the same story. So that's another form of the Gibbs-Thompson. That's sometimes called Hoffman-Lorentz equation. What else? This just, I'm not sure why these two are here, but basically this is just showing kind of the energy difference and actually it's not really right because the critical size gets 1/2 as big. So homogeneous versus heterogeneous, the peak is at 1/2 the size. So it should have been that the red one peaked over here. And then it's roughly like half or 1/10 of the height. So the height would even be lower than that. So basically that's just showing the two energy barriers to nucleation for homogeneous, heterogeneous. This thing is for homogeneous nucleation because it's R cubed. So basically you could rewrite this and get a Hoffman-Lorentz for heterogeneous nucleation if you wanted. It would be kind of the same form. And it would be the same form because this equation would be the same. This would be R squared times T. This one would just be R times T. So actually everything falls out except you have a T left over in this thing. So it'd be a thickness term in here for the layer that you built, but otherwise its form's the same. So anyway, this is from another book. So it's just people are using different symbols in this. So this is from the surface science book, and they use 5 for here where it's F. So it's the same. Hopefully you can see these things are the same equations. Like the point of putting these in here is that it's people use different terminology for the same thing. And then this is from that Adamson physical chemistry book. It's the same thing. Just showing that there's the same derivation like over and over again for that thing. So this So the rate, yeah, so when you have homogeneous nucleation, it depends. The overall growth rate of crystallinity is going to depend on this free energy drop, so the driving force for it. And then it's also going to depend on this nucleation rate, and that nucleation rate depends on that barrier energy. So if you have the barrier energy, this delta G max, and you can get the nucleation rate for the growth of the crystals too. So this whole picture of having a peak in the free energy allows you to decide like what the rate of nucleation is going to be. And this delta G depends on temperature. So whatever temperature you crystallize at, then you get different nucleation rates, and you also get different driving force for growth. So it's basically there's a balance between the nucleation rate and the driving force for growth to give you like a maximum crystallization rate. Like if you're at a shallow quench, if you're at a deep quench, then you get a large nucleation rate. So this I nucleation rate is big at low T. And then the delta G, for the transport part, the diffusion part's low at low T. So it may swap out at high T. So you have basically, if you look at the crystallization rate versus temperature, and it's zero when you get to the T infinity. As you quench down further, it goes up because of this nucleation rate's going up and the growth rate's going up, but the transport's going down as you cool down, and that goes like that. So you end up with a maximum in the growth rate from crystallization. That's related to this nucleation thing going on. Anyway. 3 forms of the Gibbs-Thompson. So I went through those. That's kind of that business. So anyway, so the other thing, that's one thing I want to go through. Any questions on that stuff? That's what the homework is on, that nucleation stuff. There's a paper. So you have to kind of derive that. This paper's on nucleation at interfaces between grains and a metal. And he's using this Gibbs-Thompson, or the basically that nucleation growth rate thing. I'll go through that tomorrow. But anyway. So let's see. So this is a gas absorption machine. So it's a separate subject. So this is like how you measure the surface area. So people make like, you're gonna make some particles, you wanna know their size, right? So there's a variety of ways to get their size, but one common way is to put that in a vacuum, right? And then pump in a small amount of like nitrogen, and the nitrogen sits on the surface of this, of the particles. So you lower the temperature, nitrogen condenses under the particles. And then you raise the temperature and then the nitrogen goes off. You measure how much, like, grams of nitrogen or something come out. And each nitrogen has like I think it's like 8 angstrom footprint. So if you have the number of moles of nitrogen and the size of the nitrogen, you can figure out the area of the nitrogen covered on the surface. And then if you divide it by the mass, you get the like meters squared per gram number. This would be the mass of whatever material, the powder that you put into it. This is a machine that does that. It's a gas absorption machine. So it's like a workhorse for materials. So you put liquid nitrogen in the dewar, stick your particles in there, stick it in there. It's going to condense the gas on it. Then you wait for a while to reach equilibrium, then you pull it up and it degasses from it. And so that's basically the idea of this business. So when you analyze that, so you'd see that there's a change in the surface coverage with the pressure that goes into this. So you're going to get a curve like that. That's a typical thing. So the amount absorbed, this is like the moles of nitrogen that absorbed versus the pressure of the nitrogen we fed in. So it's gonna have this like kind of plateau shape to it. So that's like the characteristic of it's called a linear absorption. So basically you have the number versus pressure and goes like that. That's a linear equation. So this is called surface coverage phi. So phi isn't surface coverage. Phi is the surface coverage. Oops. Phi surface coverage. Oh yeah, phi's got to do with the pressure. Yeah, that's right. Phi is the pressure times Ka over 1 plus Ka times the pressure. Linear equation. That's basically you have a surface and you're covering it with whatever molecule you have. And this is the fraction versus open sites. So and how much of it covered the surface. There's a picture of it here somewhere. Like they have you have your molecule coming in, which would be nitrogen, and they have a number of sites in the surface that can fill, and then nitrogen takes up some of the sites. That gives you this kind of plateauing equation. Right, at high concentrations, then the 1 doesn't matter, and this goes to 100% coverage. As you get lower, this thing drops off to 0. Like when you get A2 goes to 0, it goes to 0. So at some point, this becomes linear in concentration. So you kind of have basically at the limits, it's going to be like 0 linear. And the other point is like that. And this equation gives you this kind of thing that connects it to for surface coverage. So you see that, like, you can use that equation for a lot of different things. The assumptions of it are that you have a monolayer that forms. So there's sites. If one nitrogen sticks here, it doesn't affect the probability of the nitrogen sticking here, which some of these things are ideal. Right? In other words, if a nitrogen is here, it probably is blocking that site a little bit, but you're assuming that it doesn't. So you have equal probability to land in any site, no matter if it's filled or half filled or whatever. And then what are the other assumptions for Langmuir? No interactions between sites. Each site can only hold 1, so it's a monolayer coverage model. Then all sites are energetically equivalent. Thermine absorbs to an immobile state, so it doesn't interfere. And then it's a flat surface, right? So you do see that sometimes, like this initial stage of this is almost perfect Langmuir, but then it's got some other weird stuff that happens, right? So if it kind of does that and then goes up like that, that's the second layer going on. So you have a monolayer forms, it fills up, and then it starts filling another layer, right? So that's like type 2 absorption. So type 1 is this Langmuir absorption. Type 2 is, you can use a BET equation to describe it, or you can use a Freundlich equation, which is this thing, it's an empirical equation. Freundlich can describe a lot of different things, but it doesn't mean anything. Like it doesn't have any model with it. It's just like an equation that fits the data. Type 3 curves for that mean that you have competition between a lot of different kinds of absorption. This is monolayer. This is something like it goes bilayer and then it goes trilayer in sequence. And then this is a free-for-all absorption of all different types of layers. And then this type 4 is this is where you're talking about the structure of the pores, type 4. So weird things can happen with this. So you can have what's called bottleneck pore. So you can fill the nitrogen into the pore, and then it's got a trap, like it can't get out very fast. So the release isn't as good as the acceptance, right? So you can also have closed pores where the nitrogen can't get in at all. So you have surface area that you can't measure. So depending on the shape of the pores, these curves can have different shapes. Basically, people are understanding like understanding what's going on by the shape of these curves. And so anyway, so that's kind of this gas absorption measurement is usually you'll use the BET equation, you'll see a curve like that. If you're doing modeling of absorption, usually you use the Langmuir because the BET equation you can't really understand. It's an equation, it's this equation, it's kind of complicated. And why you get that equation is nobody, you can read about it, but nobody really knows it off the top of their head. So they just use it, right? But there is a theory behind it and the numbers mean something. Then you'll see people use this Freundlich equation, but it doesn't mean anything. So it's kind of just a free-for-all fitting function. And so anyway, so that's kind of the way this goes. So Langmuir is the simplest one. Langmuir is really the only one you can talk about, right? So there's two ways to look at it. You can look at it from a equilibrium point of view. So you have like a chemical reaction where you're starting with two components, a solvent and a solute. So one of them is dilute and one's concentrated, and the solute's condensing on the surface, and it reaches equilibrium. Right? So initially you have the surface has A2B in the bulk and A1 on the surface, and that's going to convert to bulk phase one. So the solvent's released from the surface, and the absorbent's absorbed to the surface. So you have A2B plus A1S goes to A1B plus A2S. So the equilibrium constants like that. Products over reactants, right? And then the absorbed material on the surface is this theta. That's the thing that's used for the Langmuir equation. That means the absorbed species. And then the solvent in the phase one in the bulk is almost pure. You'll have a small impurity of this thing's absorbing, so that thing's activity coefficient is 1, or the concentration you'd say is approximately 1. Right, so that term drops out. That's handy. And then you just have this theta term, which is the thing you're trying to get. And then in terms of the reactant part of it, there's A2 in the bulk, which is your starting concentration. So that's what you want to know. You want to know what the absorption is a function of the concentration you put in. That's the equation you're getting. So that thing's okay. And then A1 in the surface is going to be 1 minus A2 on the surface, because they have to sum to 100% of the surface sites. So if you plug those in and then rearrange it, you get that equation, equilibrium equation for this Langmuir absorption, which follows that curve, wherever that curve went. Just follows that curve, this blue curve. It's just like a plateau, like you're saturating the surface with the material. That's the idea. So you start out linear dependence, and all of a sudden the holes start filling up, and then there's no more holes, and you plateau out. So it's just your right, and then that's an equilibrium model for this. You can also talk about it as if it was a if it was a kinetic reaction. So that's an equilibrium model. There's a reaction kinetic model that gives you the same answer. So you just say, so let's see. There's an absorption and a desorption rate, right? And then the two rates have to be equal when you're at equilibrium. So in the absorption rates, a rate constant for absorption times the pressure of whatever the thing is, times how many free sites are on the surface, and then desorptions, the surface concentration of A times the desorption constant, and this K, equilibrium constants absorption over desorption constants, which gives you this equation, surface concentration, which is the theta, and then PA times S, and then you can, so PA times S, so S, let's see, S0 is the total number of sites, that's going to be the free sites plus the absorbed sites. So the free site's going to be from the kinetic equation. Well, you can plug in for that from the kinetic equation and get this term, and then just add those and you get that's the same as the linear function. So you can get it from this kinetic model or from the equilibrium model. That gives you this blue curve. Both give the blue curve. But then the other curve is this BET curve for the absorption. I found a paper on that, but I didn't have time to write a quiz, homework on it. So anyway, there's a lot of papers on doing this stuff. Because of this bottleneck problem, so the absorption desorption curves don't match, and the presence of a difference hysteresis between the absorption. So absorption is this smooth BET curve. Desorption is this triangle thing. Is because of this bottleneck thing. So you can they talk about the structure of the pores based on this, looking at these curves. People will write ad nauseum about the structure of the pores. Based on kind of what, so people do this just for a living, like just do gas absorption. That's all they do, and books written on anything. So that's one thing. Then, all right, so there's two other things on, and one's really short, like this. I could do that one first because it's short. It's basically, I said that when you have the correlation function, and you're at low, so you have like the binary correlation function. Oops, let me get rid of this. We have like some phase, and then we're saying we want to have rods of length R, and then like there's going to be G of R, going to be like a double sum of starting position and then to the other position like that, right? So basically there's a sum over starting position, it can start anywhere, and then ending position. I have to end the distance R away, kind of an R ending position. And then it's going to be like yes or no. Yes is 1, no 0. And then if sum goes up, then take the average of that sum, and then I'm going to say that's the G of R. So it's going to go, it'll be 100% and then it's 0. I'm just going to do like 1, because if it's at the same place, then it's always, and then it's divided by like the density. The density would be like the probability of finding it all, finding the phase all. Anyway, so it's going to be 100% when you're at 0, because it's just like the same thing as this. This would be equal to 0. And as you go out in R, this thing drops. It's just going to go down. So I said at the initial stage of this is the surface to volume ratio. And then it's going to go to a peak and whatever, dampen out, and this is the average concentration out here. Right. So anyway, because once you get to so far, and it's just like, is it in a phase or not? That's the concentration. That's just the average concentration. Right. So anyway, so the initial, I wanted to say like this, like why that surface to volume there. So if you look at it, so if you have really small R, right? If the two ends of the thing are inside, that's yes, that's 1. The two are outside, that's no, that's 0. But there's these cases where one's inside and one's outside, right? So if you said that it was the volume fraction, if you said it was the volume fraction, so this G of R should be the volume fraction. Well, if you start to consider that surface, that's still in the phase, but this isn't, then you have to say like the surface to volume, then that function is going to depend on how big R is. So the bigger R is, the more of the volume of the particle you're going to consume. You get less particles, so it's going to be minus R times the surface to volume. So that's why this function is like G of R is linear in R, and the thing that its slope is minus the surface to volume ratio. And so that's another thing about surfaces. That's one, and then one last thing here, this business. So these block copolymers, so they use this for, let me go back over here. Oh, let's see. This could have been a homework too, but. ECP. So these the block of polymers. So you can make polymers that are chains that have you have like polystyrene and then like polybutadiene. So like this guy and this guy. And you can make a block of that and a block of this. You have basically one chain going along and the other guy going along. So those more or less want to order when you get near a phase separation point, it would be like just polystyrene domains and polybutadiene. They're glued together with this covalent bond, so they can't separate. Right, so you get this problem that they're going to microphase separate. They'll try to separate, but it'll be like domains set up like one polymer and another polymer. They don't mix. Right. When you do that, you get these. You do that, you get this kind of thing. You can get if it's large of one component and small of the other, you get spherical domains. If they get kind of close to each other, you get rod domains. If they get exactly the same, you get lamellar domains. And then on the other side, where the other component takes over, you go back to rod spheres. So spheres, rods, lamellae, rod spheres, and there's some weird phases that happen too. But anyway, so the question is like, what size domains do you get from that, right? Because you're going to want to use that. You can use it for a lot of things. Like you can make tire tread with it. SBR rubbers made that way. You know, the styrene's a glass and the butadiene's a rubber, and the styrene acts like cross links for the rubber because it's glassy. But you can also use it as a sacrificial phase. So one of the two polymers can be dissolved out and you can leave with pores. Or maybe one's hydrophilic and you can swell it with a sol gel material that makes a ceramic in it. And then you can pyrolyze the whole thing and make the structure. This thing has like papers about doing that. That's the phase diagram thing. This is temperature and this is composition. Composition being the composition of the two blocks, and it's just a single component system. The two blocks, like 50% will be half polystyrene, half butadiene. Then L means lamellar, C cylindrical, and there's a spherical at the edges. So anyway, so people are using that quite a bit to make microporous materials that you're going to use the gas absorption to quantify. You know, so that's like nano structured materials for filtration or catalyst support, things like that. Like here's some pictures of kind of what those things can look like. Right. So anyway, you want to be able to calculate, like say, what molecular weights do you want to make that thing the size that you want? If you want to make an artificial zeolite, then you'd want to have certain pore size that atoms could fit through, certain molecules could fit through. So basically, you want to be able to tune that size. There's a lot going on in this. I think this is Chemical Society review, but basically there's a lot of papers on this. It's for basically ceramics. People are using this quite a bit to make structured materials like MOFs, metal organic framework materials can be made that way. Anyway, so anyway, for our purposes, like we want to be able to calculate the size of those, and this is a thing called the Helfand theory for this business. But anyway, so you write a free energy expression like our free energy expression, except it's got a new term, which is there's an entropy term that has to do with the so in this case, there's a mixing term for like the A and B. So there's a chi parameter that decides like the mixing of that, the entropy of mixing. And there's also when they go into the structure, so it's going to be like PS, BBB, So the chains are kind of stretched out, and there's a deformation. So you have some size ds, and there's a natural size for that, r0 ps. Right, so if you take basically that thing squared ln kt gives an energy. This is like a probability. So it's like a Boltzmann expression giving energy of stretching out the chain. And there's also an entropy term that affects, but because you have to localize that chain, then you can think of those chains as gas atoms that would be free floating around, but then they have to be fixed into that line because they're hooked at that barrier. There's an entropy penalty for that. So that would be this interfacial entropy change. This conformational is a stretching of the chains. And this is just a Flory-Huggins mixing, which is like the Hildebrand. It's the interaction parameter times the concentration A, concentration B. Right, so this first term is just that thing. And then this is the enthalpy of associating at the interface, which has to do with the interfacial thickness, interfacial area. So in other words, this interface between the two has an area O, we call it OP. OP. Then interfacial also has a thickness dt. So OP dt is like the volume of the interface. And so the reason he's putting in OP is he's going to minimize the whole free energy expression with respect to that. He's going to take the derivative of GP with respect to the area of the interface. He's going to get a magic interfacial area that's it's the minimum of the free energy, and that's the interfacial area that will, if you plug that back into this equation, you get the free energy, and you can also get the size from that. You get this dA dB from that. So there's an enthalpy of forcing the things to mix at the interfacial connection point. It's got to do with the volume they're stuffed into. And there's normal chi mixing of the two components. Then the entropy terms here, the interfacial is going to be that probability. So the bridging points could have been in the total gap, the A and the B phase, but they're restrained to this dt. So dt by that gives you the probability of locating the connection point there. Plug that times kt gives you the Boltzmann energy of doing that. And then the conformational term has got to do with the deformation of it. It's got to do with the square of R over R0. The square is because they're random structures. There's some reason for the square. Anyway, so you have all these terms in the unknown term, or the term that you minimize against is this area term. At least the way Helfand did it. So this is the expression, there's the area term, and you take the derivative with respect to the area, and then you set that to 0, and then you solve for the area of the thing. You end up with that expression. Then you can plug that back in and get this DAB from it. And then basically this DAB agrees with the experiment. Like you can calculate the phase sizes in this as a function of molecular weight. So basically, if you want a certain phase size, if you want a certain spacing to fill with your ceramic, pick the spacing you want, and that's the molecular weight of the components that you would need to do it with. And then this can get more elaborate. Like this is for symmetric, where the styrene and butadiene have the same molecular weight, and then you get lamellar. You can calculate the same thing for different conditions. Different nodes, if you want to get these other structures, like if you want to get rods or spheres, they've done similar analysis to it. They can do the same kind of approach. The lamellar one's the simplest one. It's just the Hildebrand kind of equation, adding in terms for this, just adding in terms where you need it, like for the interfacial position, and that you minimize against that interfacial position and get the sizes. So it's the same kind of exercise. Anyway, that's it for this chapter. That's kind of everything. The 3 Gibbs-Thompson things, this binary correlation function thing, this stuff about block copolymers, gas absorption stuff, Langmuir equation. And that's it. That's what we did today. So the critical nucleus stuff, which is the homework problem. And that's it. So any questions or anything? That's kind of what I have right now. Yeah, so next time I'll go through the homework, that other paper, kind of goes through that free energy expression thing. So